Alright, so the probability of getting exactly K successes in trial, so these are just formulas, which you will need to know, so if you want to like highlight them or mark that you're going to have to know them for the test, you can do that. But we have N things taken K at a time, which would be the same thing as the NCR. This would be just NCK instead. Of P raised to the K times 1 minus P, which would be Q, raised to the N minus K. The mean of a binomial, mu, is equal to N times P. And then the standard deviation of a binomial is sigma is equal to the square root of NPQ. Yes, I'll get it back to you when we're done. Yeah, I actually just did them last period. You did well. Is this the next one? Yeah, okay. All right, so back to the Archer problem, kind of picking it up. So our Archer continues to hit the bullseye with 80% accuracy. She shoots 200 arrows. So that's kind of the change now. Instead of 6, it's now 200. What are the mean and standard deviation of the number of bullseyes she might get? So
we use the same formula, right?
You're using the formulas we just did.
Okay, so U equals M and P.
So that'll be 200 times 0.8. You know what that is since you're so good at math in your head.
It's 160.
160 bullseyes. And then standard deviation. Yep. That's 5.66. So, is the normal model appropriate here? So we need to check the conditions for that. So our first condition would be that NP is greater than 10 and NQ is greater than 10. So we need to check that. So N times P, so that's, we already said is 160. So 160 is greater than 10. And then N times Q would be 200 times 0.2, which is 40, which is also greater than 10. So our sample size is large enough. And then we have the independence or 10% condition. So are these independent? Or is each shot independent of the next one? Yeah. So shots are independent. So we can use a normal model. So now we're throwing it back to, like, I don't even know, one of like unit 2 or something like that, to use a 68, 95, 99.7 rule to describe the distribution of the number of bullseyes she might get. So we've said we can use the normal model. So we have our bell curve here. The center of it, I'm gonna do this. Center of it is at 0. And then each standard deviation away, so that's 160 is the actual mean here. So then at 1 standard deviation away, it is basically we're adding 6 because she can't just, shoot 5.6.
I was about to say that's so it's gonna be 166.
Yeah. Then 2 standard deviations away, be 172, and then 3 away would be 178. And then going in the other direction, we're just subtracting off. So at -1 would be 154, -2, 148, and -3, 142. And so then from 1 standard deviation away is the 68%. 2 standard deviations away are 95%. And then 3 standard deviations away is the 99.7%. So this is the normal model for 160 being the mean and 5.66 being the standard deviation, but we're just going to treat that as that we just treated that as 6. So if you were to see it written that way, that's all that means. So then, would you be surprised if she made only 140 bullseyes?
Wait, only?
Yeah, like if she didn't make any more than that.
Oh, then
Yes, why?
because it's standard deviation shows that's on the lowest amount is 142. So anything below that would be like I don't know, preposterous.
So anything we usually say more than 2 standard deviations away is unusual because it's just not likely to happen, and that would be more than 3 away. So basically, since it is more than 2 standard deviations away or below the mean, that would be an unusually low number of bullseyes. And that would be the kind of the same thing with if she scored anything over 172 bullseyes, we would consider that unusual. But certainly past 3 standard deviations away in either direction is very unusual.
Do you know why they're patrolling? They got some.
And honestly, it may not have been anything. It may have just been that he's subbing down the hall. Like, really could be that. I don't know.
What was his
Huh?
what was his like little demeanor that he had?
Just standing there watching.
I'm talking about like the past few days.
Oh.
Cause they said some people said that. Like just all I said he was like this stinky.
Oh. I don't know. Sometimes it's just you can just tell. If you're like, hey! And they're, hey. Or if it's like, hey! It's like, hey, how you doing? It's kind of how you can tell.
I mean, I don't talk to him, so I don't know.
Okay. Shortly after the introduction of the euro coin in Belgium, newspapers around the world published articles claiming the coin is biased. Oh man, I forgot to bring those with me. Man. The stories were based on reports that someone had spun the coin 250 times and gotten 140 heads. That's 56% heads. Do you think this is evidence that spinning a euro is unfair?
No. Because it's a 50-50, it's a 50-50 chance.
Okay, well,
It just happens when you're happy.
let's decide mathematically if it is or not.
Yeah.
All right, so this is something where I'm going to just make this note up top. We could use a binomial model. But the normal model is easier, so that's what we're going to use. Now, that's obviously given that the conditions are all met. So we need to check the conditions. Now, I will tell you a lot of times what happens after we go through the examples. I usually just say to make a note that you've checked the conditions. Pretty much all the problems that say to use the normal model can use the normal model. So it's very rare that you have one that doesn't meet the conditions, but at least tell me that you thought about it. So normally I would just say checked conditions, bloop. But I'm going to go ahead and write them out just so you get used to seeing them, because it does come up as like multiple choice questions sometimes. So we have to check that n times p is greater than 10 and n times q is greater than 10. So basically they're saying they got 140 heads and 110 tails then, because that would mean the rest had to be tails. So from that means that both are greater than 10, because, you know, both of those numbers are greater than 10. As far as our independence or 10% condition, first we see if they're independent. Is each flip independent? Okay, yes. So since they're independent, we don't have to look at the 10% condition. If it wasn't, then we would have to look at that. But each coin flip is independent. So then we can use the normal model. And so we need to find the mean and standard deviation. So we just use the same formula that we had. So that's n times p, which is 250, times the probability. Well, in theory, it should be a 50% chance heads or tails. So we're going to multiply it by 0.5, which would be 125. Then the standard deviation would be the square root of NPQ. So that's the square root of 250 times 0.5 times 0.5. And that ends up coming out to be 7.91. So we want to know basically getting more than 140 if that is making it unfair. So kind of what we're looking at, I'm just going to draw this small. So we're looking at this curve here. The mean is 125, and then basically I'm just going to call this 8. So adding 8 to it gives me, what, 133, 141, and 149, something like that. So it's getting closer out to 2 standard deviations, obviously. So if we're just looking at it visually, we can say, well, it's technically within 2 standard deviations, so we wouldn't say it's unusual. So that's one way to look at it. The other way to look at it is the, to to find what it's called again. I always forget what it's called. Normal CDF, I think it is, where we would start at 140, then do the 1E99, then put in our mean and standard deviation, so 125, and then 7.91. And if we did that, it gives us 2.9%. So basically, there's a 2.9% chance that you get more than 140 heads, which is just very small. So the probability of, to sum this up, the probability of 140 heads is low, but not too low. So it could be unfair. But we can't guarantee that. And I would say that it could have just been very random. Since everyone is independent, that doesn't necessarily mean that, whatever. But you could have told that just from looking at the normal model. But normal CDF also shows you the percentage, which is just very low. So, next, vitamin D is essential for strong, healthy bones. Research shows that about 20% of British children are deficient in vitamin D. Suppose doctors test a group of elementary school children. What's the probability that the first vitamin D deficient child is the 8th one? Any ideas on how to set this one up? You can tell me the calculator way or the non-calculator way.
So for this one, we would use the binomial model for this one.
Pretty sure this one's geometric. Pretty sure this one's geometric, if you're going to do that. Yep. And then that comes out to be 0.042. I'll just write over here. If you were going to do it by hand, you would have failures first. So the first 7 would have been a failure, which would have been 0.8 raised to the 7th times 0.2 for the success. And then that would have been how you did it. So then the probability that the first 10 children are all okay would be what?
So you plug in PDF 0.8 and then put 10.
And which function did you say to use? Not PDF.
CDF.
Yep, CDF.
I still have trouble figuring
So PDF is if we want a up to a specific point, so like one specific thing, but CDF is when we're like adding up all of them. So I will tell you one thing is missing from this with what you said, but yeah. So it's going to be 0.2. Whoa, I just wrote literally geometric. It's help if I actually write the function CDF. 0.2, 10. But that's for,
Wait,
it's 0.2.
it's 0.2?
Because it's the success rate, which is 0.2. But we need to do.
Success rate always like a negative thing.
I know. It's why I said it's really confusing. It's like what you're looking for. Like, I don't really like that they say success failure because it's more like what you're looking for versus what you're not. But this one is that the first 10 are all okay. That's going to show you that something that basically they're not okay. So we need to do 1 minus this. And so if we do that, that gives us 0.107. The other way, if you just wanted to do it that the first 10 are all okay, that meaning they don't have a deficiency, we would have done 0.8 raised to the 10th and get the same thing, basically. So then, how many children do they expect to test before finding one who has a who has this vitamin deficiency? So what's my formula for expected value for this section? I think it was on like the very first page we did, possibly. If not, we did it in one of the problems early on.
Success.
Where did we do it? I know we did it in one of these problems yesterday. We did it in example 3D.
EX.
Yeah, 1 over P. So 1 over 0.2. You know what that is too?
It's 5.
Yeah. So 5 children. So then they will test 50 students at the 3rd grade level. Find the mean and standard deviation of the number who may be deficient in vitamin D. So what is the mean?
So NP. It would be 50 times 0.2.
Yep. Which is 10. And then what about standard deviation?
So square roots 50 times 50 times 0.2 and 0.8.
Yep. And that lovely number comes out to be 2.83. So then if they test 320 children at the school, what's the probability that no more than 50 of them have a deficiency? Huh?
This would be correct.
No. We just need a function, calculator function. So this is binom, because we don't care about the order. So binom CDF. So we're adding up. So no more than 50. So anyone from 0 to 50 have a deficiency. So it would be 320.2 and then 50. Whoops, I hit clear. And that gives us 0.0269 blah 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 So then that gives us 2.7% chance, basically, that no more than 50 have the deficiency.
That's pretty.
Okay. The American Red Cross says that about 11% of the U.S. population has type B blood. A blood drive is being held at your school. How many blood donors should the American Red Cross expect to collect from until they get a donor with type B blood? So, how many should they expect to see? That's your clue.
So you expect it, now you think so it'll be 1/P.
And P is 0.11. So 1 over 0.11.
So that's it's like 9 point something.
Yeah. It's 9.090909 repeating. So we're just going to call it 9.09. People. So then, again, with these ones, you can tell me either by hand or in the calculator, but what is the probability that the 10th blood donor is the first donor with type B blood?
So which one?
So does order matter?
Yes.
Okay, so which one does order matter for?
It's geometric.
Mm-hmm. So geometric is where order matters. And then CDF or PDF. The first one is the 10th person.
It's PDF.
Yep. So geometric PDF of 0.11 and 10. And that is 0.039. If you were going to do it by hand, you would have basically 9 failures before the 10th success. So 0.89 raised to the 9th times 0.11. And that would be equal to the same thing. So then, what is the probability that exactly 2 of the first 20 blood donors have type B blood?
So it would be the first two. In other words.
Well, no, so it's saying it can be any 2
Oh, okay.
of the 20. So it could be the first 2, it could be the first and the last, it could be the 2 in the middle, it could be the 5th one and the 12th one, it doesn't matter.
So it would be geometrics.
Order doesn't matter. If order matters, it's geometric. If order doesn't matter, it's... Yep. PDF or CDF? Yep. Because we want a specific amount. And it'll be of 20, it's 20 trials, probability of 0.11, and we want 2 of them. So that is .282. Now again, by hand, we would have 20 things taken 2 at a time, so 20 C2. Then 0.11 for the successes. We had 2 of them. Then 18 failures, so 0.89 to the 18th. So if you were going to do it by hand, there it is, and that's what the answer would still be. All right. What is the probability that at least 2 of the first 10 blood donors has type B blood? So when we see at least, what do we think? Okay, well, yes, that's the function, but what does at least give us?
It's a compliment.
Yep. So we're going to do 1 minus the binom CDF for none. Or for 1, I guess, technically is what it should be. For 1. So 10.11 and 1. Because that's less than 2. Because at least 2 means 2 or more. So we should take out that. So that accounts for 0 to 1. So if we do that, 1 minus 10.11. That comes out to be 0.303. So if you were going to do this by hand, you would do 1 minus, and then it would basically look like this, but for 0 and 1. So you would do 10, 0, and then blah, 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 and so on and so forth. So anyways, I would just do that by calculator. The blood drive has a total of 150 donors. Assuming this is a typical number of donors for a school blood drive, what would the mean and standard deviation of the number of donors who have type B blood?
So for me, it would be 150 times.
You want to take a guess, or you want me to just type
I'll
it
say
in? Okay.
So 10.1 is 15. So I'm gonna go. I'm going to say this is. No, it's I'm getting so close to that, but it's 16.5
Yep.
for real.
Yeah. That's people with type B blood. And then the standard deviation.
It's 150 times 1 times 0.89. And no, I would not solve this.
This one is 3.83. I don't feel like writing the words again, so I'm just going to write ditto marks. So then, surprised by the low number of type B blood donors at the blood drive, the American Red Cross wonders if the 11% estimate was too high for your area. How many type B blood donors would it take to convince you that the estimate might be too high? So, N times P and N times Q are both greater than 10. So, I don't have to worry about that. 10% condition, 150 people is less than 10% of the entire population of people. So we're good there. Now, obviously, each person's also independent, so we could account for that as well. And then out of the 150, 16.5 people had type B, meaning that 150 minus that 133.5 did not. So basically, if we were to look at the chart, the mean was 16.5. Now, I'm just going to subtract off basically, 4. So 16.5 minus, I'm just going to do 4 to make it easy. So it'd be 12.5 minus 4. This would be 8.5. Minus 4 would be 4.5. So basically, if we see anything less than 9 people, we would say that the estimate's too high, because that would be more than 2 standard deviations away in the negative direction. So if we saw less than 9 people, it could be considered too high.